Hello everyone, in this demo I will demonstrate how users will benefit from DistFax. Before the tool demonstration, let me give you some backgrounds and context. Distributed software systems have been increasingly developed in recent years because of the more and more requirements for many computation tasks. The target of my research is common distributed systems which have the following properties. First, the component of a distributed program concurrently executing on physically distributed locations, and they are executed as processes on runtime. Second, commonly there is not a global clock within the entire distributed system. Third, importantly, these components communicate through interprocess communications. Lastly, these softwares are usually very large and complex. All of these are characteristics of distributed systems. Like other software systems, distributed systems suffer from information flow security vulnerabilities. And dealing with these vulnerabilities can be even more complicated due to these properties. The quality of distributed software is very important because they widely serve as various society services, such as banking systems, web search, airline management system, medical networks, and so on. In software measurements, there are many two types of metrics, static and dynamic. Static metrics are relatively easier to compute but not suitable for measuring the dynamic behaviors of the software. Dynamic metrics complement in that regard, and they are more precise than static metrics. Given the importance of IPC in distributed systems and the advantage of dynamic metrics in this work, I focus on measuring IPC through dynamic metrics for distributed systems. In order to measure IPC, our work focuses on the interprocess communication and quality distributed systems, important aspects of their runtime behaviors. Our tool computes two kinds of IPC metrics. Among the coupling metrics, there are runtime message coupling, runtime class coupling, class central coupling, interprocess reuse, class communication load. And among cohesion metrics, there are process level cohesion. All of these metrics together capture the IPC behaviors of distributed systems at runtime. First, let us look at the RMC matrix. In distributed systems, there are many messages passing among components. RMC measure the runtime message coupling. The more messages, the higher RMC. It indicates the runtime interactivities among system components and communication costs. It could be used for assessing the understandabilities of distributed systems. I compute RMC at both process level and system level. The process level RMC between two given processes, PI and PJ, the numbers of messages sent from one process to another process. Based on process level RMC, the system level RMC is the average of all process level RMC. So suppose there are n processes, I have n times n minus 1 interprocess pairs. An example of computing the system level RMC. In the figure, I suppose the server sent 3 messages to the client and then received 2 messages back from the client. So the process level RMC from server to client would be 3, and from client to server would be 2. So total process would be 2, n would be 2. Then the system level RMC is 2 plus 3 divided by the 2 here, so it will be 2.5 here. The next IPC matrix I introduce is RCC, runtime class coupling, and measures IPC coupling in terms of the extent to which methods from a class in one process rely on or interact with methods from a class in another process. RCC indicates functional interdependency. It can be used for assessing maintainability. I define and compute RCC at class level, process level, and system level. The class level RCC is the ratio between of two numbers. The numerator is the total numbers of methods in the first class that is depends on any methods in another class in a different process. The denominator is the total numbers of methods in any process other than the first process that is dependent on, and any methods in the second process. Here, the DSM denotes dependency sets of a method M. Based on class level RCC, the process level RCC for a pair of process Pi and Pj is the sum of RCC between any two classes across two processes. Further, the system level RCC matrix is the average of all process level RCCs. So overall, the n times n minus 1 pairs of processes given the n processes in the system execution is measured. To illustrate the computation of RRC, let us consider an example here. In the table, I suppose dependency sets of method exercise in three processes are shown. SC is the server class, CC1 and CC2 are two client classes, and the union set of all methods dependency sets for P client SC as shown in the figure. The next line is the union set of P server CC1. Therefore, I can compute the class level RCC for P server SC and P client CC1 by 2 divided by 5, and I got 0.4. Similarly, RCC for P server SC P client CC2 is 1 divided by 5, and I got 0.2. RCC for P client CC1 and P server SC is 2 divided by 5, and I got 0.4. And RCC for P client CC2 and P server SC is 0 divided by 1, so I got 0 here. Then I compute process level RCCs. RCC for P server and P client is 0.4 plus 0.2, so the result is 0.6. And RCC for P client and P server is 0.4. In the end, I compute the system level RCC as the average of all process level RCC. In this case, it is 0.6 plus 0.4 divided by 2, so the result is 0.5. The CCC matrix class central coupling is similar to the centrality of a network, a matrix in network measurements to identify the most important nodes. Accordingly, it may be used to identify functionally highly important classes in interprocess executions. Thus, CCC can be used as a functionality correctness matrix. I define CCC at two levels, class level and system level. The class level CCC for a class A in process Pi is the sum of all RCCs of all possible class pairs where one class is A and other in a process other than Pi. The system level CCC is the mean of class level CCC measured for all classes overall processes. Now let me use the same example as used before for RCC illustration to illustrate CCC. For the class level CCC for the SC class in the server process, the computation is 0.4 plus 0.2, so 0.6 here. Similarly, CCC for P client CC1 is 0.4, CCC for P client CC2 is 0. Thus, for the system level CCC, I have the sum of these class level CCC 0.6 plus 0.4 divided by 3, I got 0.33. The fourth IPC matrix I introduced is IPR, interprocess reuse. The idea is to qualify functionality overlapping and co-reuse in terms of IPC coupling. I define and compute IPR at method level and system level. The method level IPR for a method M in a process Pi is the ratio of the intersections of the local dependency set of and remote dependency set of M to the size of the entire set of covered methods in all processes. The system level IPR is the ratio of the sum of the method level IPR measures overall methods in system execution. to the size of the entire set of these methods. Let us consider the same example for IPR illustration. Suppose I have LDS, the local dependence set, RDS, the remote dependence set, and M, the entire set of covered methods are shown. The size of M is 7, so the three method level IPRs are 1 divided by 7 because of the size of the intersection between LDS and RDS is 1. The system level IPR is those 3 divided by 7 and divided by 7, which is 3 divided by 49. The fifth IPC matrix I introduced is CCL, class communication load. The idea is to measure the communication loads of an individual class communicating with others in all remote processes. I define and compute CCL at class level and system level. The class level CCL for a class A in a process PI is the ratio of sum of the sizes of remote dependent set of the class's method to the size of the sets of all executed methods in the class. The system level CCL is the mean of class level CCL measured over all classes executed across all processes. Let us consider the same example for CCL illustration. Suppose I have RDS, the remote dependent set, and M, the entire set of covered methods as shown. The size of M is 3. So the first class level CCL is 3 plus 1 plus 1 divided by 3, which is 1.67. And the CCL for CC1 client is 1 plus 1 divided by 2, which is 1.5. So the system level CCL is 1.67 plus 1.5 divided by 2, 1.585. The last IPC matrix I introduced is PLC, process level cohesion. The idea is to measure internal connections within an individual process. I define and compute PLC at process level and system level. The process level PLC for a process PI is the ratio of the sum of the sizes of local dependent set of the processes methods to the size of the set of all execute methods in the processes. The system level PLC is the mean of process level PLC measured over all processes. And let us consider the same example for PLC illustration. Suppose I have LDS stands for the local dependent set, and M, the entire set of covered methods as shown. The size of M is 3, and PLC for P server is 3 plus 2 plus 1 divided by 3, which is 2, and PLC for P client is 3 plus 2 plus 1 divided by 3, which is 2. So the system level of PLC is 3 plus 3 divided by 2, which is 3. DistFax uses 5 quality metrics: execution time, cycle complexity, information flow path count, information flow path length, and attack services for different quality characteristics and their relevant subcharacteristics. These quality characteristics performance efficiency, maintainability, and security, and subcharacteristic time behavior, modifiability, testability, confidentiality, integrity, non-repudiation, accountability, and authenticity refers to the standard quality model ISO IEC 25010. DistFax takes two kinds of inputs, including runtime input T of the system and the distributed system itself D. With these two kinds of inputs, out2 goes through 4 phases to compute IPC matrix and also provides quality classifications of the system. And more, DistFax has 4 phases: instrumentation, tracing, characterization, and classification. The first phase instruments the system to probe methods for monitoring method execution events. And after that, in the second phase, during the tracing, DistFax performs the execution of our original system. While the system is executed, DistFax traces and records execution events in the trace. DistFax also computes different quality metrics including execution time, cycle complexity, information flow path count, and length, and attack surfaces. And based on execution events, DistFax has the characterization phase. This phase computes all 6 IPC metrics which was shown before in the previous slide, including RMC, RCC, CCC, IPR, CCL, and PLC. Using these IPC metrics and quality metric results, DistFax computes the correlations. In the last phase, DistFax utilizes learning-based classifier to predict the high-level status of the quality matrix of distributed systems. The output of a classifier is one of the two categories, high or low, indicating the system quality being abnormal or normal. We use Python programs to perform k-means clustering and supervised learning with holdout validations, and tenfold class validations for classifying quality metrics from IPC metrics, and we use WCAT to perform back-end supervising learning to classify quality metrics. The evaluation results demonstrate the correlation between IPC metrics and quality metrics, and classification effectiveness, including precision, record, and F1 accuracy. And you can get the tool from the address here. And thank you for your attention and time.